Good morning, everyone. It's my pleasure to share my research work on GNSS urban navigation on smartphone, virtually from China. I'm Han Gao, working at Raymond Lab of Huawei Technologies in China. So today, my presentation will be about integration of shadow matching with road information for improved mobile urban positioning. I would like to acknowledge my colleagues to accomplish this work. The presentation will comprise 4 parts. The first part, introduction, will have a quick overview of the urban positioning problems on smartphone. The second part will have a brief introduction of the shadow matching algorithms and its problems. The third part will introduce my research work to improve the basic shadow matching algorithms in several domains. The final part will present the experimental performance on smartphone in Shanghai. In urban canyon, the tall buildings will produce signal blockage, non-line of sight reception, and multipath interference. For signal blockage, less satellites are received for positioning. But nowadays, this problem can be mitigated by introducing more constellations with more frequencies. The positioning errors due to multipath is typically about 10 meters. So, among these three, the unlost reception is the most serious one for positioning and navigation. This is an example. The below figure is a piece of data collected on smartphone in deep urban in London. There are many unlost signals received via the reflection from the surrounding glass surface of tall buildings. The positioning results with pseudo-range is poor. It can be seen that the unlost receptions can cause errors as large as tens of meters. The shadow matching algorithm has been developed to improve urban positioning based on the signal visibility if a satellite signal is an lost or unlost satellite signal. The basic idea of shadow matching is to match the signal visibility from 2 aspects. The first aspect is the satellite signal visibility measured from the GNSS raw measurements, such as signal noise ratio values in most publications. The second part is the satellite visibility predicted from the 3D building models. If the signal will be directly visible from the satellite to the position candidate of the search area. The basic shadow matching algorithm comprises 5 steps. The first step is to determine the search area. A search area is initialized centering on the conventional GNSS solution, such as the weighted least square solution or the extended Kalman filter solution. The second step is to predict the satellite visibility from the 3D building model. And the third step is to predict the satellite visibility from the GNSS measurements, their observation. The fourth step is to score. And for the search area, each candidate position will be scored by considering the matching between their observed and the predicted visibility of all satellites. The 5th step is to position. And the position with the highest score or the average position over all candidate points weighted by their score is determined to be the shadow matching solution. However, there are some problems coming with the shadow matching algorithms. I summarized them into 4 points. The first one, the search area influences efficiency. If the search area is too small, the true point, the ground truth, is in danger of not falling into the search area. However, if the area is too large, there will be a very heavy computation load for mobile devices to run in real time. The second point, the prediction of line of sight or non-line of sight signals from signal-noise ratio is not reliable. We know that the reflection from glass surface of tall buildings may sometimes produce unlost signals with very strong signal-noise ratio. The third point, shadow matching algorithms sometimes produce ambiguous solutions. So the below figure is an example. 2 points, the ground truth and the points on the other road, they both have very high scores. This is due to their similar signal visibility predicted from the satellite measurements. This happens especially in the urban scenario with single-sided streets or the street junctions, and also the urban area with streets distributed densely and parallelly. The fourth point, the shadow matching algorithms always show better across street than along street positioning accuracy, and this is due to the line of sight and non-line of sight their distribution. In the next part, I'll show how to take use of the shadow matching algorithms only along the across street direction. To mitigate the problem, we made some efforts to improve the shadow matching algorithm. The improvements include the following part. First, to use the machine learning algorithm for more accurate lost or unlost satellite visibility prediction. The second one is to take use of the multi-epoch filtering to fully take use of the historical positioning solutions to reject outlier. The third part, to use the road information and map matching algorithm to mitigate the ambiguous shadow matching solutions. The final part is to take use of the solution of shadow matching algorithm on a cross-street direction for better same-street side identification, and this would benefit plenty of location-based services in urban, such as Didi or Uber taxi pickup and pedestrian navigation. I will go to details of these improvements in the next slides. This slide shows the system framework, how the shadow matching algorithm has been combined with a common filter. After initialization, the transition model is built for pedestrian and vehicle based on contact detection results used for state prediction. Then, the state of the filter is updated based on pseudo-range and Doppler measurements received by each satellite. If the building model is available, it's supposed to be the urban area. The shadow matching will be initialized based on the updated common filter solution and output its own solution, both on along and cross-street direction. And finally, the cross-street results of the estimated position state will be corrected based on the shadow matching solution for more accurate and reliable across-street solution. This figure shows how the algorithm can be run on a smartphone for real-time implementation. The ephemeris and building model are deployed on the cloud server. The raw measurements can be calculated from the Android API and downloaded ephemeris. The positioning solution and the algorithm can be run on the smartphone, not on the server side. The building model and the road information will be downloaded beforehand in a compact format, and all of that will be kept in local. For Shanghai, which is a very big city across the world, the size of the building model and road information will be about 200 megabytes. For the GNSS measurements and the user's positioning results will all keep in local, will not be uploaded to the server. I'll introduce the improvements one by one. So the first improvement is better initialization. we initialize the search region with the filtered Kalman filter solution. The filtered solution for initialization is more precise, as the fit-in solution not only contains the predicted state of the that is corrected by shadow matching, but also updated by the filtered loss satellite measurements. And the search area is adaptive, it's not fixed. The search area, the search radius, can be set based on the position variance, which can be estimated from the filter solution. The second improvement is to use much smarter classification algorithm and more satellite measurements for loss and unloss classification. We know that the classification from solely signal-noise ratio is not reliable, so we train a neural network and use it to make more accurate prediction of loss or unloss signals with more satellite measurements. This include pseudo-range residuals, elevation and signal-noise ratios, and so on. Is the probabilistic outputs of the neural networks will be helped to score in the next stage. The third improvement is important to use the road network information. The road network information has been useful in this research in two aspects. The first one is to identify the best matching street from the candidate area to avoid ambiguous solution. We can see from the below example that there are multiple candidate points on different streets. They both have very high scores, so it's very hard for the shadow matching algorithm to pick up the true point. Is here. But after selecting the road 1, the true street, the true point of among the candidates can be easily picked up. The second is that the road direction of the best matching street can be helpful to update the position state based on the shadow matching algorithm later in the filter. We can only update the filter can only update its position state only across street, not at the along straight direction. The fourth improvement is made on position determination. The shadow matching algorithm output a solution based on the top 30 highest candidates on the best matching street, and also the positioning uncertainty can be estimated from their score distribution along different street directions. The shadow matching output can be used and combined in the Kalman filter. Its positioning solution and error variance can be used for updating position at cross-street direction. Based on Bayesian rule, the loss probability of each satellite at current epoch can be calculated from the high-scoring candidate points and the visibility predicted from the 3D building model on each point. And the loss probability of each satellite can be used to filter out the unlost satellite in the filter at next epoch, so that the Kalman filter solution will be less contaminated by the unlost signals. The final part will present the test performance of the proposed system in Shanghai. The test devices is a Huawei Mate 40 Pro smartphone with high silicon GNSS chipset that can receive satellite signals from 5 constellations with dual frequencies. The test scenarios include different urban scenarios, including bilateral street scenario, single-sided street, and street junctions. I'll introduce one by one. This slide shows the performance on a bilateral street. We can see from the figure that the green point indicates the ground truth position. The red points indicate the positioning solution calculated from a conventional extended Kalman filter, which is off the road, far from enough for urban positioning. The blue points are the results from shadow matching solutions. They have very good cross-street positioning accuracy, but very poor on the along straight direction. The yellow points are the solutions of with both shadow matching algorithm combined with the Kalman filter, which is near to the ground truth point. This also happens on the single-sided street. The conventional solutions are very far from the ground truth point. The shadow matching have very good across-street positioning accuracy, but very poor on the along straight direction. But the filtered method its result is more concentrated and more near to the ground truth point. The road junction is a challenging scenario, as we have to positioning at the right corner of the street. The shadow matching solutions are only on the right side of one street, but not on the right quarter of the street junction. We can see from the yellow points, most positioning results of the proposed method fall into the right corner of the street after filtering. The proposed method has been tested in Shanghai in different locations and different urban scenarios. For each test set, we visit 3 times, so each visit can be treated as an independent test. For the time complexity, for each epoch, the algorithm will take about 50 milliseconds on the Huawei smartphone, which is enough for most real-time implementation. For the performance, the proposed method and the improved shadow matching algorithm improve most on the bilateral streets and street junctions, which are more than 20% improvements on the same-size street identification. More test performance in other cities can be found in the paper. That's all for the presentation. Thank you for your listening and welcome to any questions and comments.